Math meet went well.
It's not all
We as a school did not place. Connor Schuler got 5th for the juniors. What? He had 25 out of 40.
I go to those things and I don't yeah. Like literally like they all just calculators.
Okay. I need your attention, please. Chapter 2 is where we actually officially start calculus. So chapter 2 I do break into 2 parts.
So does that mean that we don't have a whole unit chapter test? We have 2 tests?
Yes. I break into 2 parts. So it is 10 sections. So the first 5 sections, which mainly focuses on limits, that's going to be the first test for chapter 2. And then the second part is where derivatives are introduced. So that's the second part of chapter 2. And then looking ahead, even for first semester, chapter 3, we then get into specific rules for derivatives. So it's kind of all limits and derivatives from here on throughout the rest of the semester at least. So we don't officially start limits right away in 2.1. We have the tangent problem, and then tomorrow we're looking at the velocity problem. So these are 2 problems that introduce the idea of what a limit is. So the tangent problem, ultimately what your goal is to be able to do is to be able to approximate the slope of a tangent line using slopes of secant lines. So you might be familiar with the vocabulary tangent and secant from geometry with circles. Can anybody describe to me what a tangent is to a circle? Dylan?
It's a line that intersects the circle and is exactly parallel to the circle. It intersects perfectly with it.
Yes, I know what you mean. Did you have a different way to word? Yeah, so it is intersecting a circle, but only at that one point. So say this is the point, so the tangent would look something like that. And you can think of then, we talk about tangent lines to curves throughout this entire class. So you can think of the tangent line to a curve as being the same thing. Actually, I'll draw this on here, and that way it's actually part of this. So if you have a circle, when you were in geometry, this was the tangent to a circle. So you can think of the tangent line to a curve having that same type of property. It's going to intersect the curve or touch the curve at one point. Although, however, with curves, it's a little bit different. If you extend that tangent line out, it might end up intersecting at a different point on the curve, but when you're in close proximity to that point, it's only touching it at that one point. And then what about the secant for a circle? How is that different from a tangent? If you remember secant. Yeah, secant is basically just a line that goes through it, so it's going to intersect it twice. So even extending from here, this would be like the secant of a circle, so it's going to intersect it at more than one point. So the terminology is similar from geometry, but now we're focusing not on specifically 2 circles, but 2 curves. So I do have that definition. A tangent to a curve is a line that touches the curve. Another way we describe the tangent line, it is going to have the same direction as the curve at the point of contact. So it's a way to show the direction of the curve at that point. So we're going to start off right away with an example. Find an equation of the tangent line to the parabola y equals x squared at the point P, which has coordinates 1, 1. And writing equations of lines, whether it's in slope-intercept form, point-slope form, because we work with tangent lines all throughout calculus, you'll be writing equations of lines the entire year. So to write an equation of a line, right now we have this one point. What do you need in order to write the equation of a line? If I want to write in slope-intercept form, I need a slope. What do I need in order to find a slope? 2 points. I have 1. So if you're trying to find the slope of the tangent line, we only have 1 point. We need a second point that would ideally be on the tangent line. But if we're trying to find the tangent line, we don't know another point on the tangent line at this point. So I do have on here first we need to find the slope of the tangent line. So what we are going to do, and if you want to make a note here too, to do this we need 2 points. And right now we only have 1. So this is kind of the why we're going on to that next step. So we need 2 points. We can approximate the slope of that tangent line by choosing a nearby point, Q, on the parabola and computing the slope. So M with the subscript PQ is just the slope of the secant line PQ. So if we're choosing another point that's actually on the parabola, because then we can get an exact point with coordinates that would exactly be on the parabola, then we can calculate the slope between those 2 points. And that would be a secant line because it's going to be going through the parabola twice. So we're going to choose points for Q such that the x value of Q is close to the x value of P. So I do have our choices here. So right now P has the ordered pair 1, 1, or the coordinates 1, 1, so the x coordinate is 1. So I'm going to say first I'm going to choose a point Q that's going to have an x coordinate of 2 because 2 is really close to 1. So on the parabola, if I go to where x is 2, this is where the point Q is that I would be talking about first. I'm just going to put Q1 there. And now I can calculate the slope between these 2 points. Now that's again going to be a secant line because it's going through the parabola twice, but we're getting an approximation for the tangent line. So if I wanted to calculate the slope, first of all I need to know the y value at this point. So to find that, I can just substitute the 2 into the x squared since it's on the parabola to find the y coordinate. So if x is 2, the y coordinate is going to be 2 squared, so 4. And I'm just going to put Q sub 1 by that since I had labeled it on my graph. And that way you know what points we're talking about. And so between this point and then our point P, which has the coordinates 1, 1, I'm going to calculate the slope using the slope formula. So change in y over change in x, I would have 4 minus 1 over 2 minus 1. So 3 over 1, or just 3. So the slope of that secant line would be 3. Okay, so I know that is not equal to the slope of the tangent line. The tangent line is going to be a different line, but it's an approximation. I'm thinking right now the slope of the tangent line is close to 3. I know it won't be exactly 3, but it's close. I can get an even better approximation if I choose a point Q that is even closer to the point P. So this point is pretty close. It's only 1 unit away in terms of the x coordinates, but it's not as close as I can possibly get. So now, instead of choosing the x value 2, I could have chosen the x value 1.5, and then it's only half a unit away from the other point in terms of the x. So looking at that on the graph, so if I were to look where x is 1.5, so this is where my second choice of Q is. So you can see that point is even closer to point P. And now this ordered pair then will have the following coordinates. The x coordinate is 1.5. The y coordinate, again, substituting this into y equals x squared, since it's on that curve, to find the y value, would be 1.5 squared, so 2.25. And then between that point and, again, our point P, which is 1, 1, I can calculate that slope. So again, another change in y over change in x. So I would have 2.25 minus 1 over 1.5 minus 1. So 1.25 over 0.5. And this slope ends up being 2.5. So I could also be drawing these secant lines in. Maybe I will, at least for these two. I was going to see if I had a straight edge up here, which I do, just so you get the idea of what's happening. So here's our first secant line, which we said had a slope of 3. Now here is the second, which has a slope of 2.5. But what we're seeing is now these secant lines are going to be approaching kind of where the tangent line would be as that value of q gets closer to p. So 2.5 is a better approximation. It's still not exactly equal to the slope of our tangent line. So I could get even closer to point P. I could have chosen the x value to be 1.1. So now I'm only 1/10 of a unit away in terms of the x values from point P. So on the graph, if I start drawing these in, it's going to look super close. I might draw this one and probably not the next two. But approximately here is where my third choice of Q would be. X was 1.1 on the parabola. So if X is 1.1, then the Y coordinate would be 1.1 squared, so 1.21. That's my third choice for Q. And then P is still at 1, so now I'm calculating a new slope. So change in Y over change in X, 1.21 minus 1 over 1.1 minus 1. So I have a 0.21 over 0.1, so 2.1 is the slope. Okay, maybe this will be the, I know I said this the last time, maybe this will be the last one because this one actually too would show up pretty nicely. If I were to draw the secant line here, I can see that's even closer to what I would think of as the tangent line to P, just touching the parabola y equals x squared at P. So hopefully you're getting the idea. I could say, well, I can get even closer than 1/10 of a unit away in terms of the x values. I could make it 100th. I could make it 1,000th. So we're just going to calculate these next year. I'm not going to put them on the graph because they're super close. So it's just going to look messy if I try to draw them both in. But this would be like a fourth choice of point Q, which is going to be even closer to point P. It's only, in terms of the change of the x values, 100th of a unit away. So if x is 1.01, then 1.01 squared for the y coordinate is 1.0201. P is still 1, So now if I calculate that slope, change in y over change in x, 1.0201 minus 1 over 1.01 minus 1. So that's 0.0201 over 0.01, which is a slope of 2.01. And the last one I have for you, now if I got even closer, so now I only want to be 1/1000th away in terms of the x value, so the fifth choice of Q, if x is 1.001, if I square that value for the y value, that's 1.002001. I'm obviously not rounding those. And then P is still 1. So last slope to calculate You might already be getting this idea, change in y over change in x, 1.002001 minus 1 over 1.001 minus 1. So that's 0.002001 over 0.001, which is 2.001 for the slope. Okay, so there's 5 slopes for 5 different secant lines that could be drawn in. I had only sketched in 3 of them before it would start to become messy. But the idea is that the closer you choose an x value to the x value of P, then on the actual curve, the closer that point Q gets to point P, meaning the idea is the closer the slope of the secant line gets to be the actual slope of the tangent line. And you're defining that idea of a limit, what value are you approaching? So it looks like as Q is getting closer to P, like I said, the closer the x coordinate is to 1, and the closer the slope of the secant line is to what value? What value are we approaching here? 2. So this would suggest that the slope of the tangent line should be 2. And again, it would be considered the limit of the secant slopes. Okay, so now, do you need to, like we found 5 here, use 5 different values of Q and 5 different slopes every time if you're choosing those values? No. However, these last 3, I would say don't just say use the value that's going to be 1/10 of a distance away or 100th of a distance, or go straight to 1,000th of a distance away and say I'm just going to use that one value, and whatever value I get, I'm going to use that as my approximation, or say, well, that's really close to 2, so that must be it. You need to at least, I'd say, look at 3 different values to see what you're approaching, because it's possible that there may not even be a limit. So I would really need to at least look at these last 3 values here to see, okay, yeah, it really does appear that I'm approaching 2. Because if it doesn't appear that you're actually approaching a number, then there may not be a limit. So once you have your slope, though, the whole problem was asking us not to just find the slope, but to find the equation of the tangent line. Now we can write the equation, because we have a slope of 2, and we have the point that our tangent line was going through, which was our point P, which had coordinates 1, 1. And you have reviewed this already. You had to write the equation of a line on your test. So ultimately, whatever form your equation is in the end doesn't matter to me. If you were to use point slope forms, that's the y minus y sub 1 equals m times the quantity x minus x sub 1. I could just substitute my slope and my point in here. So that would be y minus 1 equals 2 times the quantity x minus 1. And I could leave that as my answer, and that is absolutely fine. You will see equations of lines given to you in this form in calculus. You could also, sometimes you'll see equations like this where they won't distribute anything on the right side, but they will add this value over to solve for y. So you might see it written this way, y equals 1 plus 2 times the quantity x minus 1. That would also be an acceptable way to write the answer. You could also just write it in slope-intercept form, so distribute the 2 and simplify. So if I did distribute 2, that'd be 2x minus 2 here, and then combine like terms, so that'd be y equals 2x minus 1. So 3 different ways you could give the answer. What I'm trying to say, though, is aside from this first answer, these other 2 are being simplified using algebra. So that's not calculus that's getting you to that point, it's algebra. So if you were to have this as your answer, and then you wanted to rewrite it into slope-intercept form and you did that incorrectly, now your answer is just wrong on the AP test. So it's better almost on the AP test to just leave it like this if it's true response versus try to simplify it, because you went from a right answer to a wrong answer, now you don't get points. So there's going to be kind of some back and forth. Do I simplify? Do I not? Because You don't want to lose points on the AP test, but if it's multiple choice, they're going to give you answers in simplest form, so you almost have to know how to simplify and then just kind of choose whether or not you need to do it when you have your own problems for the free response. That's getting further into AP formality stuff. But are there questions on this example? It's just a little bit of a process, finding secant slopes to see what your tangent slope would be based on that limit. So I have that more formally written on the back side. So as I've said, we say the slope of the tangent line is the limit of the slopes of the secant lines expressed as, and this would be how we write limits. So the slope of the tangent line is the limit of the slopes of the secant line. So how this limit is written, or how to read this, I should say, it says the limit as, and underneath, the limit as Q approaches P. So the limit as Q approaches P of, and then I'm just going to write the slope of PQ here, but remember, this is representing the slopes of the secant lines. Is, and then M, which M is representing the slope of the tangent line. And normally with limits, you're going to see values in there, not all variables like I have written here. But again, so the limit as Q approaches P of the slopes of the secant lines, M of PQ, is the slope of the tangent line M. So just showing that that slope is considered a limit. That's the big idea for this. So then I have one last example, and this one is a little different because the function we are working with, we do not have an equation for, and you do not need to find an equation for it to find, in this case, what the slope of the tangent line would be. So it says the flash unit on a camera operates by storing charge on a capacitor and releasing it suddenly when the flash is set off. The data that I have here in the table below describe the charge Q remaining on the capacitor, which is measured in microlooms at the time t, measured in seconds after the flash goes off. Use the data to draw the graph of this function and estimate the slope of the tangent line at the point where t is equal to 0.04. So ultimately, that's what we're trying to find. And I did add a note. It was given within the problem because at this point, we're not necessarily asked to interpret. We're trying to find these limits first. So the slope of the tangent line in this scenario represents the electric current flowing from the capacitor to the flash bulb. So that's what it's representing. But ultimately, we're trying to find the slope of that tangent line. So we have our different times. We have our different charges. So I'm just going to sketch, rather plot these points, and then draw a curve through them and sketch what the tangent line would look like. So this is just kind of a visual for you. Some problems might ask you to estimate the slope of a tangent line from a graph, where you'd be estimating the rise over run, and we could do that for this one, but because we do have the specific data points given in the table, we don't need to. There's a better way to find it since we have the specific points. But I do want to show so you can see visually what this actually means. So I have the 5 points plotted, 6 points, there's not 5, there's 6. And then if I were to draw just a curve through them, you could definitely, on your graphing calculator or any graphing software, plot the points and then find the regression equation to get a curve. That would give you an equation to use as well, but it's not needed. So ultimately, where t is equal to 0.04, that is the value of p, or the point p that we're talking about. If I kind of correlate with P from the other example. So we want a tangent line to this curve at this point. So I know I didn't tell you to grab a ruler, not that you really needed one, I'm just using one on here, but what the tangent would look like, so it's going to intersect the curve at P, but it's just touching the curve at P, so it's going to be under this curve based on, we haven't talked about concavity of a curve yet, but concave up is where it would have more of a parabolic shape. So this is what the tangent line would look like at that point, approximately, showing the direction the curve is headed at that point. So from this table, when you're given just a table of points to find the slope or estimate the slope of the tangent line, in terms of choosing points Q, and Q in this case, don't get confused with the Q that's representing the charge, but choosing points Q, we can't necessarily choose points as freely as we did in the previous example because we don't have, say I wanted to choose the t value 0.03, I don't have a function to plug it into. So I wouldn't be able to say what that y coordinate or the q coordinate is like I could in the previous example. I could choose whatever x value I wanted to that got close to 1 because I could plug it into the function to get the y value. I can't in this case. I can really only choose the points I'm given. Yeah, if I found the regression, I could do that. You don't have to do that though, or you're not expected to do that. So rather than doing what we did in the last example, I'm just going to label my point P here at 0.04. What I can do is on either side of P, choose the point Q that's closest on either side. So I could choose, when the t value is 0.02, to say BQ1, and then also on the other side, I'll call that Q2. The closest point is when the t value is 0.06. And I should have said this in the previous example. I'm just going to flip to that example quickly. Just to specify, I chose values of x that were getting closer and closer to 1 that were also bigger than 1. I could have approached 1 from the other side as well. So not to confuse you, but I could have started, like 0 is also a distance of 1 away. I could have started there and then had my point Q move up the curve towards P. So that is why in this instance, I'm looking at the point that is closest to P on either side. So I'm just going to put here for Q sub 1. So this is the point, 0.02 and then 81.87. I can find the slope between this point and my point P, and that would give me one slope as an approximation for a secant line. So if I calculate that slope, my change in y's, or my change in q's in this case, would be 81.87 minus 67.03 all over 0.02 minus 0.04. And then, so calculating that would be a change of 14.84 on top, and then a negative 0.02 in the denominator. So that would give me a negative slope of negative 742. So that's one slope. That would be an approximation. And I'll just draw that in that same color of blue so you can see how it compares, the secant line between those 2 points. So I found the slope of that blue line You can kind of see on my drawing how it compares to the the tangent line that I drew in pink. And then for the second choice of Q, so now this is the point 0.06 and then 54.88. Sorry, I'm kind of writing sideways here. So the slope between this point and P, change in the Q values or the Y values would be 67.03 minus 54.88 all over 0.04 minus 0.06. So that's a change of 12.15 over a negative 0.02. So negative 607.5 is another estimation. Yep, and that would be, if I drew that in, that secant line would be here. So you can kind of even see on the graph that our tangent line, the one I drew in, is in between those two secant lines, meaning you would expect the slope to be in between these two values. So the best approximation we can get, not finding a linear regression or not even linear, but just a regression formula, not finding that because you're not expected to do that, would be to average these. If I average these, that's the closest approximation I can find.
How do you know where to put
You're kind of estimating where to draw it, so when I draw it in, I'm making sure that I'm only touching the curve at that one point P, and that it's kind of showing the direction the curve is headed.
So it doesn't matter like how you do like blue, you could do any circle.
Oh, these ones were specifically, so the blue one was through the point P and through this point. So I actually drew it through those 2 points. Yes, yep, if you're drawing in the secant line. And this was just to show you the tangent line is in between, so the slope should be in between their slopes as well. So if I average those two slopes, does anyone have what that is? So the tangent slope averaging negative 742 and negative 607.5. So add them together, divide by 2. What was it? Negative. Thank you. All right, does that make sense? Now realize the difference between the two examples again. I know I might be repeating myself a lot with certain things, but it's the idea behind it. Because really all you're calculating slope and you're writing equations of lines. Okay, you've learned both of those things in algebra. It's the ideas of what to do with those calculations that's important. So note the difference between the two examples. The first one, you actually have a curve. You are choosing your own x values that get closer. Versus in the second one, you only have a table of data. This would be a numeric representation of a function. You're only given a table. One thing that you might also want to jot down, there's another way to find this exact same value in one step versus 3. So rather than find the slope between, say, Q1 and P, and then Q2 and P, and then average them, this is the same, or you would get this same value if you just found the slope between Q1 and Q2. So rather than doing 3 steps, I just wanted to show you because that's why it's working out that way. I could have just found the slope between Q1 and Q2, because that would be a change in y of 81.87 minus 54.88 over change in the x, 0.02 minus 0.06. And you can double check, but if you found this slope, you would get the negative 674.75 in one step. So either way you get there, it doesn't matter to me, but just noting that you can find that same answer either way.